So just to keep, so we know where we're going, because sometimes it's a little calculatory. We will first do some introduction, some preliminaries, just to fix the settings. Second, I will continue these preliminaries with some basic definitions that we have seen already, but we will need them to recall them. Just notion of resonance. Okay, so the second, after this short preliminaries, we just go back to the notion of dispersion and introduce coordinates that are called symplectic coordinates, or symplectic complex coordinates, that are a change of variable that allows to have a very nice form of the Hamiltonian, especially the quadratic one. I will also give the definition, what is the notions of resonances. And the other thing I need to recall, because Poisson brackets. Okay, and then I will do 3, and I will introduce the Birkhoff. So Birkhoff normal form, which will be of third order, and that will correspond to a first change of variables. That essentially will eliminate all cubic term in the Hamiltonian, and then I will discuss the fourth order. That is second change of variable that will show us that we will see that when you truncate the Hamiltonian at order 4, the only term that remain will be lead to what we will call partial integrability. So as we go along, we will define these words. Okay, so that's the plan. Okay, so just remind you. So now we're going to work on our domain is the two-dimensional domain, but we will concentrate in a situation where x is in the torus, and y is between minus infinity and eta of x and t. Okay, so it's still deep water. In deep water, a lot of calculation become kind of very simple. It's not the case in finite depth. Although these formulas can be, some of them can be extended even to the 3D, the formula are not so simple and beautiful. So it's nice to present it in this case. And so because we are on the torus, the Hamiltonian is defined, and 1 over 2, I put 1 over 1/2 integral x. And so with our system dt eta xi equals j, that matrix 0, 1, minus 1, 0 of the gradient eta xi of h. And because of, so we will assume that eta and xi are periodic in the variable x. Okay. And because of the context of this periodic setting, we will be led to work with their Fourier coefficients. So we will denote eta k, the Fourier coefficient, 1 over 2 square root. And the same for xi. And the same for xi. Okay? And because the mass is conserved, we can always assume that we will always can assume that the zero mode is 0, right? Because it's the integral. And as we see in the Hamiltonian, the zero mode of xi does not appear. So we can also assume that xi 0 is 0, the zero mode of xi. Okay. And because this is a DDN, if you like. So if you add a constant, you can always change xi by removing the constant. Okay, and so the other thing is that so it is convenient then to rewrite our problem in the Fourier components, and the system can be written in the following way. So sometimes I will forget to put the hat, but when there is a k downstairs, it means that it is a Fourier coefficient. So in Fourier space, the system can be again written in the form. So I can write it. Derivative of h with respect to xi k, eta k. So you see, this is a xi k. So this means that we imagine that we have written the Hamiltonian in Fourier space, and it is again Hamiltonian. So I think this is not evident, but in papers it's always done like this. So I think for those who have not seen it, so that means that the transformation from real functions to their Fourier transform or their Fourier coefficients is canonical, right? Doesn't change. So if you want to verify that, you have to consider, because you see there is minus k. Xi and eta are real. So there is a relation between the Fourier coefficients, and if you want to prove that this is true, starting from there, you will need to consider the transformation eta bar. So I did it once in detail. You have to work together with eta and well, I think you have to count somehow twice eta xi to eta bar k, eta bar k. I did not write it very correctly here. Okay, I'm not writing correctly, but anyway, there is a way to prove it. I'm not going to. I will write it maybe tomorrow correctly because I don't have it clean here. Anyway, this is in Fourier space. The problem writes like this. And now, what else we want to say? We are interested in small solutions. So we will be led to consider the expansion of the Hamiltonian in powers of the variable eta xi. So since we know that G is analytic in in eta, since we know that the Dirichlet-Neumann is analytic in eta, that leads to an expansion of H in powers of eta and xi. So the first term is quadratic. Okay, so that's the setting. And then it is convenient to rewrite these quantities in Fourier coefficient, in terms of Fourier coefficients. So H2 is going to be so 1/2. So we read it. We read it from here, 1/2. Okay, of k ck square plus g eta k square. Okay, so we are in a periodic domain. So the Fourier coefficients are discrete like this, and everybody sees that because at the leading order, if you remember, G0 is the Fourier multiplier D, which in Fourier space means absolute value of k. So the first term is this one, the quadratic term, and then you go along with the next one. So it's 1/2. And we can remove the zero mode. K1, K3. So we will need these formulas, that's later. And xi hat K1, eta hat K2, xi hat K3. And we need H4 if we want to go to the fourth order, but we don't need it to write it immediately. Well, we are this theory is under the assumption that you are expanding the Hamiltonian in powers of the eta and xi. So this is in the context of small solutions. Yes, there is convolution. I should have written it here. K1 plus K2 plus K3 equals 0. Thank you. Okay. Yes, so it is in the context of small solutions. Okay, so what we are looking for canonical transformation that will eliminate terms in the Hamiltonian. We look for a sequence of transformation that will remove, if possible, all terms that are non-resonant in H3, in H4, etc. That's essentially the. So let me write it. Maybe we look in words. We look for canonical transformation the canonical transformation from the original variable to new variables, where all non-essential, so we'll have to define what this means, non-linearities are eliminated. And we will ultimately, I mean that we will go up, we will not go to any order, but theoretically the idea is to get a new Hamiltonian. So a new Hamiltonian will be H2. So H2 will remain, but we will have what we call Z3 etc. Zm plus a reminder. Plus a reminder. Okay, so each of these z is homogeneous in eta and xi, in the new variables, in the phase space. And so Zm, Zj, homogeneous of degree j. Okay, in the same way that H3 is homogeneous of degree 3, H4, etc. And these Zj are what we call resonant terms. And they will satisfy. So that's the term that we have not been able to, we are not able to remove. And they satisfy the Poisson bracket of H2 Zj. So we will see how this condition comes up, but this resonant term will be those that satisfy this relation. So if you remember the Poisson bracket, we will recall it in a minute, a little bit later. Okay. So what was so what I said the other day, and yes.
Must be satisfied by the solution of the equation for each state
This Zj that remain satisfies with so let's say I do a first transformation at order 3. I have eliminated a number of terms in H3. I have only Z3, and the Z3 will have satisfied this. Now the yes, but at each stage, right? So you do it in sequence. You first do it, let's say, for Z3. So you are left with Z3. So that means that you already have first change of variable. So now you work with your new variables. You repeat the sequence.
My question is H2 on eta xi.
So it will be so at the first stage, it will be A2 of eta xi, Z3, yeah.
For eta xi solution of the problem or for all eta xi?
No, for solution of the problem. For solution of the problem. But then after I have done it once, I have new variable, I'll redo that if I can. And okay, so the result, at least on the formal level, is that Z3 equals 0. So you can eliminate all the cubic terms. And for Z4, there will be will have a special form that we call integrable. So sometimes you will see people talk about partial integrability, partial because it's only at order 4, but at order 4 it's integrable. So I will need to explain these words, and as I in a minute, but as I mentioned the other day, that was the work of Dyachenko and Zakharov, 94, and also Craig and Wolfork. But for some time, these results remained at the level of calculation, and I will do the calculation for you. But very recently, there is a paper. There is an abstract, kind of short summary, and the full paper by Berti, Feola, and Pusateri, and they were the result, this partial integrability is a consequence. Their work provide a rigorous justification of this observation that were formal in the context of results they proved. So they consider I will not write the full theorem, but they consider small, so they consider this setting of a periodic, the problem of the water waves for infinite depth and periodic condition, boundary condition, and they assume that the initial conditions are small, that in some Sobolev space, let's say of order epsilon, I don't write the precise condition, but and they were able to prove that they remain small for a time of order 1/epsilon 3. And I think that this was the first result obtained in this context of periodic boundary conditions. So it was quite a big progress. Now I would like to mention in this context of partial integrability, there has been recently a paper by C.J. Wu, and one can see her. So what she was doing, it was 2022. So her work was completely in a different setting of this, completely different. But she proved that she proved a long time existence. So in her case, it was the whole domain, in R2. So it was not periodic, but she proved a long time existence for initial conditions. And her the main result in this setting was that the initial condition was so the interface was small, the eta was small, for eta small, but she did not require no condition on the slope of eta. Okay, so that was a condition only on the function, not on the slope. So she allowed it some corners. And the reason that I think this work is in relation with that, and I think she presented also like this, is that to prove this, she did a sequence of transformation. So she did a sequence of transformation, and she got at the she obtained some modified energy. So modified energy. So I write it Ej. So dE dt. So because there are many steps, which is quite complicated. But was interesting, the reason that this is in relation with that is that the ddt of E was O of e to the power 5. So it's as if she had also removed all terms of lower order by this sequence of transformation. But it was not in this context of Hamiltonian system, because the context in which she developed these ideas is that she has the domain of infinite depth, and by conformal map, she sends the domain to half a plane. Okay, so that's the context of her work. Anyway, that was another. I think it is in relation because she was indeed able to manipulate this. Okay, so now maybe I would like to say one word about this. What does that mean, integrable? So, where is it? Yes, so when we talk about, so I can erase this, I think. So in our context, we will work with new variables zk, which will be a combination of eta and xi. So I just what it is. I'm not going to define immediately, but it's a little combination of eta k. These are coefficients. We'll define them a little bit in 5 minutes or so. But what is interesting is that if you want to so in this setting, the Hamiltonian system writes dtz equals I dzk dh over dzk bar. Right? A little bit like Schrödinger. And what does that mean? What does that mean integrable? So it's convenient to introduce to write z equals p amplitude and angle. Amplitude and angle. So square root of p. Okay, so that's the angle. And this is action usually called. And so pk is exactly zk. And the Hamiltonian system, so that's a general comment, right? A general definition. The Hamiltonian system is said to be integrable if, when we write it in, so we write it in terms of theta and p, okay, so we transform in these coordinates in terms of the action and angle, and in this, if this is 0, so if this is 0, if this quantity is 0, we can immediately see that pk of t equals pk of 0. And so from here, we see pk is constant. And from here, since pk is constant, then theta of k varies linearly, like theta k 0. Okay, so theta varies linearly, and p is constant. And if p is constant, you can prove that all the Sobolev norms of zk. So from here, you can see that the zk in Sobolev spaces equal to sigma. So what do we write? Zk 1 plus k, right, in Fourier space, S. Because the zk are constant, well, let's put here, zk. Because the zk are constant, these are conserved. So all so that's why it's called integrable. Because these are independent of time. Okay, so this is that I hope I will get to the calculation to show you that when we go to Z4, the only term that remain will be terms depending on on the action. So the action will be the zk. Okay, I hope to do that. Good. Okay, so I can, maybe that was a little introduction to put us in the context. And now let's prepare our notations and our to perform this transformation. Okay, and as we will see how this comes up. Okay, I can continue. So maybe I can not waste this space. Okay. Okay, so the dispersion relation, of course, we have seen it already. Dispersion relation, it is related to the linear problem. So the linear problem is simply g of 0 xi and dt xi. Okay. In Fourier space, it's very simple. It's dt eta hat k equals d k xi k. Okay, and when we solve this problem, we find that we have the solution in the form eta k of t equals e to the power I omega k of e to the power I omega k of t omega k omega t etc. But omega must be equals to gk. Okay, so that's the dispersion relation. Okay. Okay, so that's now the variable that will allow us to perform this calculation in a very systematic way will be this what we call the complex symplectic coordinates. Because it's in these coordinates, it is in these coordinates that we'll be able to solve this easily, this equation. This equation is a priori not simple, right? It's a equation for the Poisson bracket for two functional with so it's, but in this coordinate it will be essentially diagonalizing this condition. So what are they? They are the form zk. So if I write them in Fourier, and I and it's convenient to work also with z. Yes. Oh, I'm missing. Sorry. Yeah, thank you. It's the same definition, yes. And the other one is it's convenient to write also z bar minus k, or z if we want to put the hat, z bar like this. And if we use the fact that that eta and xi are real, there is a relation that eta hat k minus k is related to the complex conjugate. So I should say what is ak. Ak is g k 1/4. Okay, so this is ak eta k minus I ak minus 1 ck bar. So you see AK is symmetric in K. Okay. And in this, so the transformation eta K, xi K, gives zk, z minus k, is symplectic, is canonical. It's canonical. It is from here. So let me explain from. It's canonical. So I will explain from here. Where does this come from? It is so. If let's rewrite. Let's look at the H2 here. You would like to diagonalize that somehow, and if you are using these coordinates, you obtain that H2 is simply sigma over k, non-zero, of omega of k z k square. So if you remember yesterday, we had this integral h u square plus g, I don't remember exactly, but something like that. And this, remember we had some transformation, and that led to integral of r square plus s square. That's the same idea. And by the way, you see the square root of the fourth square root. It's for the same reason. So that diagonalizes the system, and in Fourier space, it's just a linear combination by coefficient. So to check that you remember that the J for the new the new J was essentially the product of the old J by the Jacobian of this transformation. If I call it this V, K, and WK. These Jacobian are simply constant matrices. So you write this constant matrix multiplied by the J that we know, and this constant matrix adjoint. And this product gives you exactly 0, 1, minus 1, 0. Okay, if you want to see it, you want to see it? No, it's okay. But yeah, so that's just a this transformation is simple because simple is just a multiplication by a constant matrix. So I'm going to erase this. So we have the dispersion relation. We have this coordinate that will be very convenient to solve equations. And what should I do more? So in particular, so in this, if I rewrite this equation, or the one, if I rewrite the equation that was in Fourier modes for eta and xi to that in zeta, in z I mean, then it becomes, so that will be our equation. I have to be careful with the eyes. So you have to imagine Z h written in the new variables, dzk. Okay, so that's our new Hamiltonian system in these coordinates. Okay, so what else we need? We need the Poisson bracket, so we defined them the other day, but we will need them in the xi eta coordinates and in the zk coordinates. So that was 2 and 3 will be Poisson brackets. So first, in terms, so you remember, we write if k and h are two general functional, from the phase space to R. We define the scalar the Poisson bracket. There are always worries about the signs, but I think this is good, correct like this. So that's in the physical space, and you can translate that in the Fourier space. Because this, we will essentially live in the Fourier space. The eta k, but we have sometimes to be careful. dk d eta k bar. So this is a definition for the k and h real functionals. Okay, and if you want to rewrite the same quantity but in Fourier space, assuming eta and xi real, because they are real, so we can use the correspondence between the Fourier coefficients. This translates in this way. Okay, xi k eta k bar. No, I made a mistake. Yeah, xi k. Oh, no, xi k. Okay, and we xi k. This is eta k, xi bar k. Xi bar k is like, they are real, right? So they are real. And then if you want to write this again in terms of the zeta, z, because this is what we will indeed use, then it becomes 1 over I. It's a little bit heavy, but to write all this, but dzk1 dk dz minus k2 minus d so I hope it is okay. Okay, so I hope there are no mistakes. I think it's correct. Okay, so that's the Poisson bracket in these symplectic coordinates. We need them. And so this is 3 and 4. will be the notion of resonances. So we will say the following. In complex symplectic coordinates, so in these coordinates of z, we say that the monomial, so zk1, zk2, clac, 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 zkl, z bar kl plus 1. So soon, instead of writing zk1, I will write z1 because it's z. We say that that this monomial of degree m, okay, this monomial of degree m is resonant if we have the following relation, that k1 plus k2 plus etc. km equals 0, and omega k1 plus omega k2 plus omega kl minus omega kl plus 1 minus omega km equals 0. Okay. We say that this monomial is resonant if we have if in this sequence of KL and KM, we have these relations. So the first important lemma. Omega is here. So if the K, all these K are in this relation, the corresponding monomial is resonant. So, for example, for our case, for the 2D water wave problem, deep water, there are no triplets with remember that K1, K2, K3 are different from 0. Each of them is different from 0, such that K1 plus K2 plus K3 equals 0, and K1 plus or minus K2 plus or minus K3. So there, and that's you can check that by hand, right? That the integer, we look for integers, positive or negative, so that this is true at the same time. And this will be the key reason why the capital Z3 that I defined earlier is 0. It doesn't exist. Okay. Okay. So that's the end of our little tools. And now let me define normal form, Birkhoff normal form. So here is the question. So that is section 3. Birkhoff normal form. So we will look. So we look for these transformations that will be canonical transformation that will whose goal is to eliminate non-resonant terms. Okay, so we look for canonical transformation. So tau from W equals eta xi gives W prime. That will be defined in the neighborhood of eta xi equals 0. So that is done for small data, small element of the such that the Hamiltonian such that in these new variables with h prime of W. So later we will eliminate, okay, and such that, well, again h prime of W. So if we look for the first one, it will be if you look for the first one, the goal is to remove all cubic terms, except those that are resonant. And the Zj, H2, such that. So the Zj are the Z3 are the resonant term. We will see there are none. Okay, but that will be the first transfer. The first. So in our first effort, we will have H2. We will have eliminated cubic term. And so how do we construct that? We construct this transformation as, so we construct this transformation as flow. So the transformation, this mapping tau is the one-time flow of so this will be obtained from a transformation, from a one-time flow flow to an auxiliary Hamiltonian. What does that mean? K. So let me explain what this means. It will mean that to go from W to W prime, we will solve a Hamiltonian system. We will solve a Hamiltonian system associated to an auxiliary Hamiltonian system and auxiliary time. So more precisely, we will have to find K. We will have to find a Hamiltonian K such that so we will have so it will be this is a Hamiltonian system with an auxiliary Hamiltonian, an auxiliary time, and in this situation we'll ask that psi, the solution of this problem, at time t equals 0. t equals -1, it's W, and at t, it's S0. Okay. So there is an auxiliary time. At time t equals 0, it's my initial condition, it's my variable. And so the transformation tau that associates to this, oh, it's S. I mean S. Okay. So that's a Hamiltonian system which consists at time, this is a new time, this time is not the same time, it's S, right? And the transformation from S equal 0 to S minus 1 is that transformation. So it's a canonical transformation. This method is called the Lie method. And this provides, so we will have to find this K, right? We will have to find this K. Okay, is it clear? It's a not usual. So, at the I mean, I don't know if it. I always make mistake with the order. SZ equals 0. What? You can put it like this. At that time t equals 0, at S equals 0, it's the old solution. And at S equals -1, it's the new solution. Well, psi is a solution of this flow. It's a flow. Psi is at time t equals 0, psi is W, if you like, at S equals 0. But I want to say that it depends on W. It depends on the initial condition. Mm. Okay, so it's a Hamiltonian flow. At the initial time, at the initial S, it's the old variable. At the S equals -1, it's the new variable. Okay, so what do we do with this? We're going to try to find K3. K. Okay, maybe we start and then. So this transformation, tau, will give. So it's quite implicit, right? We have to solve a certain another Hamiltonian system that we will have to find, such that in fact these terms disappear. I mean the cubic term disappears, but we can find it explicitly. How do we find it? We're going to do two expansions. One, we will use the Taylor expansion of the Hamiltonian, that one we had in powers of the space variable etaxi. And the second will be a Taylor expansion of H in respect to S. Okay, this new time. So let me write first the Taylor expansion. So, and maybe after that we have a little break and we'll combine these two expressions. So the new Hamiltonian is equal to the new Hamiltonian is equal to the old Hamiltonian of psi of W prime at S equals -1 equals. And now I do a Taylor expansion. So I do H of psi of W prime at S equals 0 plus minus dH ds of psi of W prime at S equals 0. That's a Taylor expansion in S. Plus 1/2. S equals 0. Plus, 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 plus. So we'll do first a Taylor expansion of this type, and we're going to calculate each of those. So this one is exactly H of W prime. The second one, we will, this one, so always have to be careful with the signs of psi of W prime at S equals 0 is equal to integral psi. Yes, because it depends on you. When you solve an initial value problem, the solution will depend on the initial condition. This is in this spirit that. When I do my Taylor expansion near S equals. Let me see. At time S equals 0, at time S equals 0, it is there's always a little. Let's do the break. So we'll fix the prime and the no prime. So to come back to that question, we fix the primes, and it's what coming back to Mathieu, phi depends on S, and you can see psi S as a function of the initial condition. And okay, so I think we fixed these notations, and in this so this is a Taylor expansion. From there, the first term is exactly H of W prime. And then we remember the definition of the HDS. So what is it? Integral from 0 to 2 pi of dH d eta prime, d eta prime ds. And Vincent told me that we could have stayed, we could do it in the other variable, the symplectic coordinates, but it doesn't matter. We just do it in eta xi. It will be just identical. Dxi prime dx. Okay, so that's the definition, and from this and this, it is the new variables, right? So this is exactly dk dxi prime, and this is dk with a minus d eta prime. So at the end, this dds, this is a calculation we did earlier, maybe in a different context. It's the it is the Poisson bracket of k. This k we have not calculated. We don't know yet what it is, but we will find it later. And if you do two derivatives, so you will then, I don't do it again, I don't do this calculation, not to make additional mistakes, but it will be, I repeat, etc., etc. So we have a formula here. Okay. And what is important is that here we have h of w prime. So now let's return to let's put together this Taylor expansion in power of s relative to s, and the expansion of h with respect to the variable. So I will just write it to clear. So remember, we have h, let's not write variables. This is the expansion of the Hamiltonian in powers of the phase, of the variable in the phase space. So h prime of w prime equals h prime of w prime. So I'm going to take this formula. When I say h of w prime, I write h2 plus etc. Plus. Now this one, well, it comes with a minus. It comes with a minus, and it is here. So it's Poisson bracket of k, but now h. H of what? H of w prime. But h of w prime is this. So what do we write? So k. Oh, by the way, for those who were outside during the break, there was square root here missing because it's omega. Right? Sorry, there was some square root. H2 of w prime. So I write it below for a reason. We will see. Okay, minus w prime. So this minus is still minus. Plus, and let me write the next one, because at some point we will need it. K, comma, K, H2. Oh, okay, right. All right. So let's examine all these terms. What are the order? So this is second order for sure. In homogeneous of second order, because it's H2. This is H3. So it's cubic. This one is cubic. Now what about those? Well, if the goal is to eliminate cubic terms, so somehow we would like to eliminate this one. Okay. So let's make a little calculation. If this Hamiltonian K is of order m, and if H is of order n, what can we say about the Poisson bracket? So the Poisson bracket, you have to differentiate one, so you're losing one term. So the Poisson bracket becomes of order m plus n minus 2. Okay. So if we were able to, so if we choose k of order 3, we would have. So if k is of order 3, Okay, and H is of order 2. Okay, so if M equals 3, N equals 2, that gives me order 3. Okay, 2 plus 3 minus 2, that makes 3. So if we are able to find the K3, so that if we are able to find the K of homogeneous of degree 3, such that this term equals this term. So maybe I'm going to write this sentence. If we're able to find a functional K of homogeneous of degree 3, such that, so if we find K, so I write K3, so homogeneous of degree 3, such that H3 is equal to K3 H2, then we will have eliminated the terms, the cubic terms in H. Okay. Okay. Is this oui? Because the goal is to eliminate in the Hamiltonian as many terms as we can, and we are at the level of 3. Okay, so if I find, I will show that we can eliminate all of them, meaning that in this new variable, my Hamiltonian will be H2 plus a modified H4, right? Modified because this K will induce new terms, but plus R5, right? So we will have eliminated cubic terms.
Yes, but what's the goal to, at the end, to show long time existence or something like that?
Well, ultimately, it's to show long time existence. Of course, these transformations are not bounded, not always bounded. So, in fact, in these new works of Berti for different problems, including the one I mentioned, they combine this notion of normal form with good variable of Alinac. Okay, so that's so it's true that at the level of formal it was a beautiful observation, but now, 30 years later, it's useful for analytic purposes. Well, at least I see it like this. Okay, so we realize that this one is of order 3, but if K is of order 3, but this is of higher order, right? This is the only term of order 3. So the question is, how do we solve this? Right? K3 is hidden here. H3 is given. H2 is given, and we want to solve this equation. Okay. So how can we solve this equation? So this is when we go back to the complex symplectic coordinates. So solving, sometimes people call that the cohomological equation, K3, comma H2. That's a Poisson bracket. These are two functionals. H3. Okay, can we solve that? well, we can solve it in the appropriate. We can solve this if we return to the variable z. And for this, I will show you a little lemma. Imagine I have remember that H2 in this coordinate z is sigma of omega k zk. Okay, so that's, you remember omega, that was this very simple form for H2. And assume that, now take a, consider the following monomial. So we fix k1, k2, k3, and consider the monomial zk1, zk2, and I take, as it's an example, zk minus 3. But if we know to do that, we have, so consider this monomial, let's say, call it, I don't know, p. Okay, so k1, k2, k3 are fixed, and I consider this monomial, and I would like to calculate H2 p. In which order? No, p, H2. And I claim that if I calculate this Poisson bracket, I get exactly the same monomial, k1, z, k2, z minus k3, multiplied by omega k1 plus omega k2 minus omega k3. So the use of these coordinates allow us to diagonalize this coadjoint product with H2. Okay, so how do we do that? Well, we go back to the definition. Maybe I'll leave that for a little exercise, so we don't spend 10 minutes. And maybe Aram and Tian, if you have difficulties, I can do it with you. Okay, so if we know how to, we have this property, what shall we do to indeed solve this? Well, the method will be go back to H3, write it as all possible combination, because we have formulas for H3, so we should be able to write it in this combination of those of monomial, and each monomial divided by that. And yes, so this is what we'll do, and this is how you see how the resonance come up, because solving this will mean having this downstairs in denominator, and if you have in denominator, it should not vanish. It will be so because H3 will be integrals with k1 plus k2 plus k3 equals 0. So we need to be able to divide, and the fact there are no resonances will allow us to calculate this to calculate k3 as a linear combination, appropriate linear combination of the H3. Is it clear? So I'm going to write. Maybe I should write H3 to see how it works, and so H3 we had it some time ago. That's a cubic term in the Hamiltonian. So it's it. Lost it. So where it's H3. I had it earlier, but okay. So H3. We wrote it a little bit earlier in terms of so So K1 plus K2 plus K3 equals 0. That's the convolution. Minus K1, K3, minus K1, K3. Okay. So we see that in this sum we will have only terms K1, K3 of same sign, and Xi K1, eta K2, Xi K3. Okay, that was H3. And now each time we see Xi, we replace it by its expression in terms of Z. So in terms of Z, so this I copy. Okay, I hope I see it. Maybe it's here. I've lost it. So, sorry, I have to take it from here. Okay. So A1, AK1, AK3. You remember the notation A? That was this coefficients going from eta Xi to Z. And here we have Z1, ZK1 minus Z bar K1, ZK2 minus Z bar, Z plus Z bar. So ZK2, ZK2, Z. ZK3 minus ZK3. Okay, so that's the definition of the Z in terms of the Xi eta from before. And now you rewrite this as a combination of all sorts of monomials, right? ZK1, ZK2, ZK3, right? But it could be with a minor, with a bar or no bar, and all possible combination. And each term you invert through this formula. Okay. So at the end you find that K3, our K3, has essentially the same format H3, but with each term with a weight. The weight being this one. Okay? Is it enough explanation? Yeah? And what happens is that there is a formula. But there is a formula that I may not write in full. And the most important thing is that each time we have to find the coefficient, we have to remember that if K1, K2, there are no triad K1, K2, K3 of integers, right? And they are different from 0, such that K1 plus K2 plus K3 equals 0. And these kind of denominators, omega K1 plus omega plus or minus, everything may come up into equals 0. Okay. So we have a K3. I'm not going to write the K3, but probably in the notes there will be written. And it's possible to this gives a formula for K3. And there is in this special case of deep water, there are some simple formulas. If you so there is, let me put a proposition. So back in the original coordinates, back in the Xi k eta Xi eta k coordinates, K3 has a very special form. K3 equals, so it remains some simplifications, because there are some symmetries, and I write the formula that we're going to examine. We're going to examine and discuss. So it's the sum sine K1, sine K2, eta K1, eta K2, absolute value of K3, Xi K3. And I take the sum over K1 plus K2 plus K3 equals 0. So somehow, despite the fact that we had all these denominators that were not 0, but they were complicated, the formula simplifies to this. So it's indeed cubic, of cubic order, and it's very simple in a sense, because of and now, if you like, we can come back to the physical space. So physical space of this convolution means 1/2 integral from 0 to 2 pi. So that's K3 back into physical space. K3. So it's really, so you see this sign is like, with a little I, is like Hilbert transform. So you can put it I sine of d eta square, because this one goes with eta, this one goes with eta, right? And the K3 will go with this. So it's almost, you read it from, it's pretty simple. Right? That's the convolution, so that's the product in the physical space. Okay? And now we have K3, we can write the Hamiltonian system that defines this transformation. The Hamiltonian system is ds, so gradient okay, and remember at time t equals 0 we have the old and no, at s, and we go to s equal -1, it's the new variables. Okay. Now this formula invites us to work not exactly with eta and xi, but the Hilbert transform. So if I write eta tilde, I got Hilbert transform of eta, and xi tilde equals Hilbert transform of xi. Then this can be written as 1/2 integral from 0 to 2 pi. It's very simple. Well, I would say that it's just the simplicity of the 2D deep water. It's not the case for 3D problem, but at least it's good here. Okay. Okay. And now I could write this Hamiltonian system instead of eta xi. I'm going to write it in eta tilde xi tilde. And this transformation from eta xi to eta tilde xi tilde for the Hilbert transform is also canonical. So it doesn't change the structure of the symplectic matrix. And so it's very simple. If I differentiate respect to eta, so let's write the system, and you will recognize the equation. So d eta. So it's the derivative respect to k, the derivative respect to xi tilde. So xi tilde gives you exactly -1/2 dx eta square. That's burgers. That was a surprise. And so the flow that define the new variables are, on one hand, the Burgers equation, and the second, and for eta, and the linearized Burgers, which linearized near eta tilde for xi. And when we calculate that at the time with Walter, we were so surprised that it would be so simple that we checked many times, many times, that indeed our K3 times H2, and a posteriori we checked many times that it was indeed H3. So it is correct. So, right. So we had K3, and we checked many times. Okay. So this is the first transformation. And after this transformation, what happens? After this transformation, what is in this new variable that I still call eta tilde, eta xi, but we have to remember that it has been, we have performed the transformation. In this new variable, what is a new Hamiltonian? Oh, I leave it, okay, I leave prime, but we'll throw away the prime. But now, what do we have? We have no more third order term, but we have to, I would like to write all the fourth order terms. So fourth order term, I know we have maybe if you remember a little bit at the beginning, when we did this Taylor expansion in H, and then the Taylor expansion in eta xi, and Taylor expansion in S, we had many terms. So now we have chosen K3. So what happens in what remains? We have this one that we did not touch, but we have also, we have the K3, H3, and then we have also a term that was, this comes with a minus sign, and we have another term, well, plus, but I would like to gather all the terms of order 4. So this one is of order 4, right? Because 3 minus 1, 3 plus 3, 6, minus 2, that's 4. But we have another one, K3, comma, K3, plus. And this one also is of order 4, because we just solved this, right? This is exactly H3. So we have all the terms of order 4. Well, the original term of quartic term in the Hamiltonian, and those who popped up from this transformation. So we have -1 plus 1/2. So this gives us H2 plus H4 new. Plus terms of order 5. Okay? And what is H4 new? With H4 nu, well, it is this one. I'm going to drop the prime plus 1/2 of K3 H4. So let me write maybe ataxi. It could be, well, it was prime, but soon we're going to get rid of the prime. So let me get rid of the prime. Okay, so that's the new H4. Okay, and a minus 1/2. Thank you. Okay. So another very nice calculation, because it was a minus plus 1/2. It's the same term. The same term. So I can erase this. Okay. So now we have performed one transformation, one Birkhoff normal form. We have eliminated all the cubic terms, and we are left with, well, a quartic term and many other terms. So it is useful to examine what we have here. And what happened is that another nice simple calculation that happens in this case of deep water is that if I calculate K3 H3, right, of ataxi, so it's again a calculation. You go to H3, you calculate the Poisson bracket. It requires a little bit of effort, but what we observed is that it is equal to the H4. Maybe I write H4 old, so we don't. Here we don't. Right, that was the H4 old. It's equal to the H4 old, but instead of calculating at ataxi, it's not exactly at ataxi. It's at eta tilde xi. So when I calculate this expression, that is a Poisson bracket of K3 against H3 in this variable ataxi, I notice that in fact it has the same form as the H4 old, but the eta was replaced by eta tilde, which is this one. So it was very special, simple calculation. Pardon? Xi. 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 And yes, so where do I write it on? We have 5 minutes. Okay. And what is H4? Well, you remember what was H4, right? H4, if you go back to the definition, it is the 1/2 of 0 to 2 pi of eta of xi g2 of eta xi2 xi g2 of d, right? So what was G2? Well, it was the second term in the expansion of the Hamiltonian. And yeah, this is the old H4. Old H4. So now we have the old H4 minus the 1/2 of the is it yes, H4, yes, 1/2. Okay, so if we are courageous, we start again and say, what can we do? Can we eliminate again this transformation? And the response is yes, but we cannot eliminate everything. So I will not do the details today. I will just give you some nice information, and maybe we continue tomorrow with and decide what to do else, because I just want to tell you that if you want to find another transformation, in a sense, you will have to eliminate non-essential term, non-essential quartic term. And if you want to eliminate non-essential quartic term, at some point you will have to solve finding a Hamiltonian, an operator, a Hamiltonian flow. Well, we will have to find a K such that H4 nu. Right? You will have, if you want to eliminate the H4 nu, you will have to find a K3, a K4 that satisfies this. And solving in the same way that solving this equation at order 3 was related to the possibility of calculating calculating the Poisson product, the Poisson bracket of terms of something like this. Okay. Again, you will be led to write this new Hamiltonian in this form and see whether you can we will find omega 1 minus plus omega 2 minus omega 3 minus omega 4 of the same monomial, right? So the question will be, are there quartets of K1, K2, K3, K4 such that the sum of the Ki equals to 0 and this? And the answer is yes. Yes, because you can always take K1, K1, K minus K1 minus K. You can always take the trivial ones. And maybe I'll explain a little bit tomorrow. There will be two family of resonances. These trivial ones that will remain because we can't eliminate them. And another family of explicit relation of integers, right, that will satisfy resonant condition. But this resonance will be invisible, will not be, this quartet will not appear in H4. So what will remain will be only the trivial ones, and we'll calculate what remains. Okay, so that's kind of a miracle that the non-trivial one are not present in H4, in this H4 nu, but we still have to take care of what remains. So tomorrow maybe I'll explain that a little bit. Hmm?
So I think we skipped at the beginning that the theorem is that you can do this for any order.
No, I did not say that.
You can just do it for 3.
Well, I don't know. It is known how to do it for H3 and 4. But in one of the calculation, in one of the two papers I mentioned, I don't which, it is shown that if you go to the 5th order, there remains resonant terms.
Okay, that's what I was going to ask.
Yeah. So I think that's yeah. But you know, in this recent paper, there was this recent paper, Berti and collaborators. They work on the water wave problem with surface tension and constant rotation and constant vorticity. So they have the parameter of the surface tension, and they show that in fact you can eliminate all the except for a very small family of coefficients and they can eliminate all the resonant term. That gives a they give so then they give a long that gives them a very long time existence. That's a very recent paper. So except for a family of measure zero of coefficients, they can do that. But they do it. Well, I don't know. I can't describe because it's very complicated. I don't want to see wrong things. But it is true. This paper. The authors are. I think you can maybe find it on archive. Berti, Maspe. Oh, I am sorry. I forgot the other name. Pardon? I'm sorry. There is one more name, and it's 2022. Oui, yeah. Say it again.
Ventura? I don't know if this is the right paper. I think it is.
Yeah. Sorry. Yeah. Okay. So maybe tomorrow I explain this, and maybe I'll think what would be nice to finish if yeah. Thank you. Yes.